Swayam Prabha. Digital India. Educated India.
Good morning. Today I'll discuss on cascade analysis. The analysis of cascade is very important in development of modern axial flow turbine or compressor. I have presented here a picture from cascade tunnel test. And this is a transonic turbine, and thus you will find the formation of trailing edge shock and the reflection of shock from the neighboring blade. So here the shock appear and then reflected, and thereby it is interacted with the boundary layer forming on the suction surface. Furthermore, you can appreciate the formation of wake behind the blade. Thus, it has given a fairly good picture of flow through the turbine blade. Let's go to the discussions. The contents of the lecture are two-dimensional cascade analysis, cascade tunnel, compressor cascade, and the turbine cascade. I'll restrict today to two-dimensional cascade analysis. Let me first define what is called cascade. An array of blades representing the blade ring of the actual turbomachinery is called the cascade. Thus, cascade is an array of blades. Why this cascade analysis is important? Let me give an example. I have considered here a real turbomachineries. If we take a circumferential section as I am indicating here, and then if the circumferential section be stretched on a plane of paper, we'll get array of blades. Thus, the analysis of array of blades is very important. I'd like to give you another information that the study of two-dimensional flow through cascade played an important role in development of highly efficient modern axial flow compressor or turbine. I have discussed here about the cascade tunnel. Cascade tunnel basically is a wind tunnel. So the schematic of the cascade tunnel is shown over here. Now the air is being pushed through the series of blades as I have indicated here. I've already illustrated that an array of blades is called a cascade. So thus, as air is being pushed through the cascade, the flow will be deflected, and thereby the exit angle alpha 2 will be different than alpha 1. So here I have indicated the alpha 1 and C1 and incidence I. I'll define the angle of incidence soon. What is important here that the cascade is mounted on a turntable which can be rotated, and thereby the incidence angle can be changed. Thus, this turntable arrangement enables us to make measurement for a wide range of angle of incidence. Furthermore, the flow will either accelerate or decelerate following a turbine or a compressor blade. Therefore, the pressure at exit P2 will be different than P1, P1 being inlet pressure. So, to analyze the performance of a compressor cascade, at least one should measure the pressure and the velocity field both at upstream and downstream. That is why the slots are provided at upstream and downstream of the blade, and through these slots the probes are being inserted to measure the pressure and the velocity. With respect to the velocity measurement, both the magnitude and angle would be measured. So thus, in brief, cascade tunnel is a wind tunnel where air is being pushed through the array of blades, and we measure flow field and the pressure field both at upstream and downstream of blade. Here I have indicated a picture where a real compressor blade is mounted on a turntable. Here you can appreciate the profile of the blade, how it looks when they are mounted on a cascade tunnel. Let me state the two important points: that the cascade is mounted on a turntable so that its angular position with respect to the direction of inflow can be changed, and thereby it enables us to take measurement for a wide range of angle of incidence. Let us now consider a compressor cascade. I have indicated here the schematic where I have shown the array of blades, and the flow is passing through this array of blades. Since it's a compressor cascade, C2 will be less than C1, C2 being the exit velocity. Thus flow will be decelerated and it will be deflected. Because of this deflection of the flow, there will be a circulation gamma. Now, how this circulation is being generated, that I have explained by taking a circuit around a blade, which has been indicated by grid line. And I have zoomed that picture. I have considered at a point P on the circuit a line segment ds, elemental line segment, and B with the velocity vector. If we carry out the operation V dot ds and perform a cyclic integral, we'll get gamma. Thus, because of the flow field around the blade, a circulation is generated. I have also indicated that aerofoil is a device that produces circulation. And because of this circulation, there will be lift. Lift can be stated as L is equal to rho gamma into Cm. Cm is the vectorial mean velocity that I'll define in a minute, and rho being the air density. I have Stated here some important point where C is the chord being the approximate length of the blade, and S is the pitch being the circumferential distance between two neighboring blades. Also I have indicated here, since it's a compression cascade, P2 will be greater than P1 and that C2 will be less than C1, alpha 2 will be less than alpha 1. I will now carry out the performance analysis of a compression cascade. So I have indicated here a schematic illustrating orientation of blade, where Z is the axial direction and theta is the circumferential direction. C1 be the inlet velocity that makes an angle alpha 1 with the axial direction, and C2 be the exit velocity that makes an angle alpha 2 with the z-axis. C being chord and S is pitch, which have already been defined. Now here C2 will be less than C1, being a compressor, and Cm is the vectorial mean velocity, which I'll define in a minute, that makes an angle alpha m with the z-axis. As for the definition, lift will be perpendicular to the vectorial mean velocity, and drag will be along Cm. Now let's first consider the flow is inviscid and incompressible. I have already stated that as the flow passes through the cascade, it will be deflected, and thereby a circulation gamma will be generated, and thus the lift, which equal to rho Cm into gamma, where Cm is the vectorial mean velocity that makes an angle alpha m with the axial direction. To illustrate that, let's go to the velocity triangle, where I have superimposed both inlet and exit velocity. Here I have indicated C1 that makes an angle alpha 1 with the z-axis, C2 that makes an angle alpha 2 with the z-axis, and look, CZ is the axial component of C1, and CZ would remain constant as it is related to the mass flow rate through the cascade. Thus I have indicated here CZ1 is equal to CZ2, and that be designated as CZ. Similarly, C theta is the tangential component, so I have indicated here C theta 1. This line segment is C theta 1. I have indicated here C theta 2. C theta 2 is the tangential component of C2. Now I'll define Cm, vectorial mean velocity Cm. How? Now this line segment, which I have indicated by a green line, is del C theta. Del C theta is equal to C theta 1 minus C theta 2. Now if this line segment I have divided by equally, then P is the point that divides del C theta equally. If I join O and P, that will be my vectorial mean velocity that makes an angle alpha m with the z-axis. Thus, I have defined vectorial mean velocity and its alpha m. Now, if you take a projection from P, so this line segment is equal to c theta 1 plus c theta 2 divided by 2. Now one can show what is that gamma. The value of gamma is equal to c theta 1 minus c theta 2 into s. So lift, put the expression of gamma here, lift would be rho cms into c theta 1 minus c theta 2. Now by definition, lift coefficient is equal to CL is equal to L divided by R rho Cm square into C. C is equal to cot. Now put the expression of L here. Okay. After putting the expression of L, it will be rho Cm s into c theta 1 minus c theta 2 divided by rho Cm square into C. Now that can be simplified as Cl is equal to twice s by c theta 1 within the bracket c theta 1 minus c theta 2 divided by Cm. Now from velocity triangle here, concentrate here, velocity triangle, one can easily get c theta 1 cz into tan alpha 1, c theta 2 cz into tan alpha 2, and cz by cm is equal to cos alpha m. Put the value of c theta 1, c theta 1, c theta 2, cm in this expression, and you will get then Cl is equal to twice s by c, cz by cm into within bracket tan alpha 1 minus tan alpha 2. Therefore, for compressor cascades, we can express as Cl equal to twice s by c within the bracket tan alpha 1 minus tan alpha 2 into cos alpha m, where tan alpha m is equal to tan alpha 1 plus tan alpha 2 divided by 2. Note that S by C depend on the design of the cascade, right? Alpha 1 and alpha 2 depends on the flow angle at inlet and exit, right? And lift would be perpendicular to alpha m. Let me explain now about the performance analysis of turbine cascades. I have indicated here a schematic for turbine cascades where the orientation of the blades are opposite to that of the compressor cascade. Here C1 be the inlet velocity that makes an angle alpha 1 with the z-axis. Here the z and theta axis has been indicated. And C2 be the exit velocity which makes an angle alpha 2 with the z-axis. And since it's a turbine cascade, C2 will be greater than C1 as the flow is accelerated, and thereby alpha 2 will be higher than alpha 1. But P2 exit pressure will drop, so P2 will be less than P1. I have indicated here. As before, I have considered the flow is inviscid and incompressible, and thus because of the turning of the flow there will be a lift. The lift generated would be equal to rho Cm into gamma, where rho is the density of air, Cm is the vectorial mean velocity, and gamma is equal to circulation. To define vectorial mean velocity, I have gone to the velocity triangle as indicated, where C1 be the inlet velocity that makes an angle alpha 1 with the z-axis, C2 exit velocity that makes an angle alpha 2 with the axial direction. And here Cm is the vectorial mean velocity which makes an angle alpha m with the z-axis. I have evaluated Cm as I stated before. Suppose the line segment del c theta, which is del c theta 2 minus c theta 1 here. Look, c theta 2 is higher than c theta 1 in case of turbine. So this line segment del c theta has been divided equally by the point P here, and if I now join P and O, I'll get Cm, vectorial mean velocity. Now I can also, using the velocity triangle, I can write Cz by Cm. Cz is the axial velocity, right? That remains constant. Cz1 is equal to Cz2 is equal to Cz, say. Cz will be connected to the mass flow rate to the turbine. So Cz by Cm is equal to cos alpha m. Now, here I can write gamma is equal to S into C theta 2 minus C theta 1 for a turbine blade, and thus using the velocity triangle, I can write Cz into S into tan alpha 2 minus tan alpha 1. I can define lift coefficient as before, that Cl here is equal to L divided by half rho Cm squared into C. Now from the expression of gamma I can evaluate L. Thus lift coefficient Cl would be rho Cz S into tan alpha 2 minus tan alpha 1 into cos alpha m divided by half rho Cm squared into C. Now from here I can easily land to the expression of Cl, that will be twice S by C tan alpha 2 minus tan alpha 1 into cos alpha m for a turbine cascade. Hence for a turbine cascade, the expression of lift is given by twice S by C within bracket tan alpha 2 minus tan alpha 1 into cos alpha m. Please note that the corresponding relation for a compression cascade was twice S by C tan alpha 1 minus tan alpha 2 into cos alpha m. Further, I like to state that in reality, the flow is viscous, forming powder layer over the blade surface. and wake will appear downstream of blades. Thus, the viscous flow is the cause of drag, which in turn affects the lift. All this I'll discuss in the next section. Thank you for listening.